I welcome Dr. Krishna Moorthy was come on all the way down to KFRI. Hope you're here the first time, right?
Yeah, I'm here for the first time.
So, and she's going to deliver a lecture on a very interesting topic, seeing the forest through lasers, opportunities and challenges. So, on behalf of KFRI, a warm welcome to you to KFRI.
Thank you.
And my colleagues, the researchers of KFRI, and the prospective students from the Forestry College to join the lecture. Basically, for the past 50 years, KFRI has been trying to understand forests. So, one way of understanding forests is to divide it into bits and pieces and to study each bits. Like, for example, myself, Dr. Jitu, we are trying to study the insects in the forest. Siljo over here, he's studying fungi of the forest. Dr. Krishna out there, he's studying birds and animals out of the forest. Kumar, he's studying the microbes out in the forest. Dr. Pavan and Surya are looking at the water in the forest. They have Deepika who is studying the timber, the wood in the forest. So one way to look at forest is to divide it into bits and pieces and study each bit. And then at the end of the day, when you wish to give it to Dr. Srijit and Devu, they are the ecologists here, and they will put all the pieces together and tell the whole story. We have been doing this for the past 50 years, but there are many questions which have been answered, but there are a large number of questions which are yet to be answered. So that's the status of the science of forestry over here. The whole scenario is very complex, and then times are changing and new paradigms are coming up. When KFRI was started, the most important paradigm was the production forestry. We wanted more timber to be grown in the forest. We had the plantations, and we were all working on to improve the productivity of the plantations. And then the paradigm shifted to biodiversity. This way, it is not just timber; it is the biodiversity which holds. And then, after some time, came the big issue of climate change, and we shifted our paradigm to carbon. We started looking at how much carbon the forest can sequester. So there's large number of studies on carbon sequestration. And then finally, we had a big floods in Kerala. In 2018, we had a massive flood. It was repeated in 2019. And we understood that it is not timber production or biodiversity or carbon sequestration. It is basically the hydrology which matters. So the paradigm shifted to water. So how much water it can hold, how can be released, how can forests function to avoid floods. So there was changing paradigm happening. And as I told you earlier, we divided the whole complex forest into bits and pieces. Another way of looking at the whole forest to understand it is to use a totally different set of tools. We started using our microscopes, our lenses. We had the biotechnology department looking very closely at the genes, the duplicate sequences. We have a very good instrumentation center where equipments are there which can analyze our particles, material, identify the elements which compose it. And then we shifted over to remote sensing. Basically, because of this, you go far away and remotely sense the forest, which gives much more clarity. And it has another interesting, beautiful thing in the sense that we could also go back in time. You can have maps of maybe 10 years before, 20 years before. So you can understand the changes happening, you can have change maps. And you can also project it towards the future. So if this is the pattern, what is going to happen 5 years later, 10 years later. So that we have been doing. But then we have not yet started using lasers. We had a very small demonstration in this room long back, maybe a couple of years back, where we had an equipment which was revolving all the way and mapped all the people in the room. So we took the team to our butterfly garden, and the equipment was there, and it was doing this sensing process. But we were able to purchase the equipment, but then what prevented us was that the memory which was needed for handling the data with this equipment is so huge. The KFRI server could not handle it. So that was one simple point at which we were defeated. But we all are really interested to know your take on it, especially since I had a very brief look at your CV, And we have been working on lianas also.
Yeah.
And lianas are very dear to us because they are only there in the tropical forests. We don't see them in the temperatures. So we are really eager to hear your story and to understand how the technology can be used for answering some of the still unanswered questions in forestry. So, welcome you. I welcome Dr. Sruthi to give a better introduction to Dr. Sruthi. Thank you.
Thank you, sir. Thank you very much.
Thank you, sir. It's my pleasure to introduce our resource person, Dr. Sruthi M. Krishna Moorthy. She is a Smithsonian Pembroke Junior Research Fellow at University of Oxford. And coming to her educational background, she has a diverse background with a Bachelor's of Engineering in Computer Science from Anna University from Guindy campus, and a Master's in Artificial Intelligence with distinction in Department of Computer Science from KU 11, Belgium. And she has a PhD in Bioscience Engineering from Ghent University, Belgium. And she has been started her working as a research and development engineer in NMS Work software in Chennai. Then she moved into the research field and started working as a research assistant and research fellow at Smithsonian Tropical Research Institute, Panama, and also worked as a postdoctoral assistant at Ghent University and University of Maryland, USA. So she has also received many awards, research awards and grants from CWO and Forest Geo for carrying out her research activities. And she have a large number of publications related to the laser scanners and mostly related to the forest area. So with great pleasure and honor, I welcome you, ma'am, to deliver.
Thank you very much for the introduction. Is it okay if I stand or? Oh. Is it okay if I stand and talk, or is it better for online participants if I?
You can check whether the online participants will see this.
Okay. 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 Just for the online participants, can you just confirm if you are able to hear it?
Yes, madam. We are able to hear you.
Thank you.
Okay, I kind of prefer to stand.
Okay.
Just for the online participants, if at some point you don't hear me, please let me know because we can't see you. So then I can come closer to the mic. Thank you very much for giving me an introduction of how KL-PARI has been functioning. As Surya mentioned, I don't come from a forest ecology background. I kind of learned it on the go. I started with working with computers and I did AI. And then basically I started getting into forestry because of lasers. So the lab that I worked with, they purchased a new LiDAR, but they didn't have somebody who could actually work with the data. So that's where I came in. So I started processing the data to understand forest structure and to look at basically lianas. So my major PhD was always focusing on lianas. What I did was like, if you have a point cloud, so the picture that you see here is actually what you get from the LiDAR. So that's the LiDAR data, that's like the point clouds. So one of my main goals was to see if we can understand lianas in these point clouds. So that's where I came in, and I kind of got really into ecology after that. I started working in ecology after my PhD, which started as a very technical subject, and I kind of loved being in the forest, and I decided to stay in this field after. The aim of my talk today is mostly to give you an idea of what's possible with lasers. And of course, lasers is a very broad term. Based on where it's operated from, you have like different kinds. And I'll try to give a glimpse of what's possible and what are still the major challenges. And I'll walk you through some of the case studies where these data has been used to address really cool ecological questions, which was not possible with just the ground-based data sets. So to start with, as you gave an amazing introduction, forests are really a crucial part of all our livelihoods. And forests are major carbon reservoirs, and they are responsible for, they are essential to combat climate change. And especially the tropical forest alone like holds up almost 50% of the biomass of all the terrestrial carbon. And recent studies indicate that the forests are actually becoming a major carbon source than carbon sinks, which means they are releasing more carbon into the atmosphere than they are taking up. There's a lot of reasons for this, and we know that deforestation, fires, all these climate change events like drought, etc., are causing this accelerated carbon sink of forests. But how did we arrive at these estimates of forests becoming a carbon source of sink? It's made possible because we have been monitoring these forests for a very long time. We have set up small sample plots and we have been measuring these forests. We have been measuring their diameter and everything for a very long time. And this is very crucial to understand how our forests are changing due to climate change. And as he very beautifully put it, we started this basically from timber management, right? So we wanted to know how much timber a forest, how much how efficient a product is in terms of its productivity. That's how we started it. So we established small plots. We measured diameter, and diameter is basically just measured with the tape in the field. And in some cases, height was measured, but height is still a pretty complex and time-consuming metric to measure in the field. And species is normally measured. So these are all what you had in a forest. So you establish a plot, you measure diameter, you measure height. In some cases, you measure the species, and then you have some allometric equation, which you converted into volume or eventually the biomass or the carbon that the forest holds. So this ground-based measurement still is the crux of any of the forest forest carbon dynamics project. But at the same time, we have also been very interested in seeing if we can somehow improve these estimates, if you can somehow automate it, especially in countries like Canada or Scandinavia, where manual labor is really expensive. There have always been an interest to see, can we automate the way that we measure our forest? Can we do it somehow like faster with less manual input? And also, can we measure other attributes? What about the crown area of the forest? What about like even the height? It's very complicated in dense tropical forests. Can we somehow improve the accuracy of these measurements so that we get better and accurate carbon estimates? And the next question is, how do we upscale this? Because all these are very small plots. Sometimes it's few meters, like 40 by 40, 50 by 50 meters. Sometimes it's 1 hectare. In very few cases, we also have like 50 hectare plots, but those are very rare. So these are still very small plots. So how do we upscale these measurements to national level or global level or pan-tropical? So these are some of the questions that have always been there. And now I'm going to give you like a chronological idea of how these actually developed. So in the 1960s, especially after First World War, and the abundance of aerial photographs actually started to be used to map the forest cover. So people are using these aerial photographs to get an idea of what's the extent of forest cover in this district or in this state or in this country. But pretty much that's what you can do with these photographs. You cannot quantitatively measure the carbon, or you can quantitatively measure anything else with these photographs. And in the 1980s, you started to have laser scanners that are operated from that are operated from these airplanes. So basically what happens is you send laser pulses from the airplanes, which is basically what you see here. And these laser pulses hit forest in this case, but ideally it could be anything. Wherever it hits, it bounces off back to the scanner. And that's what you see as returns. So from these returns, you can actually estimate the vertical structure of the forest that you see here. And the first hit basically will be the top area of that particular area that's being measured, right? So the hit from here will be the height of this. It doesn't necessarily say the height of the tree. It just says that's the maximum height in this area. So that's what you can get from this laser. So one thing to keep in mind is when you operate these LiDAR from an airborne platform, the beam that you send, it's going to diverge as it hits the ground. So basically, you're probably going to get maybe 2 or 3 returns per tree. So you cannot measure anything detailed about a tree, but you know maybe a tree exists there and you can probably get the height of the tree. So this was basically used for estimating the height of forests. But even these heights can actually tell us a lot of interesting things. So for instance, here what you see is canopy height maps, basically the top of the canopy of BCI, which is the Barrio Colorado Island. It's a tropical forest in Panama. So this is a 50 hectare area, and this represents the top of the canopy of this 50 hectare area. And from this canopy height maps of airborne LiDAR, what they found was the gaps. So what you see in the bottom part is how much gaps are there. So these gaps actually tell us a lot of interesting things about branch mortality, tree mortality, so the dynamics of the forest. So you can actually see which area is being disturbed. And in case of natural disturbance, it's like tree mortality, and where is the branch fall and why is it happening? So you can really start to understand really interesting patterns of forest dynamics from this data set. And if you have like multi-temporal airborne LiDAR data, like in this case, if you can map the canopy height change, you can actually understand which areas are becoming more disturbed, which means you have a reduction in the canopy height, and which areas are actually growing well, which means there is an increase in the canopy height. So airborne LiDAR data are really cool tools to get a landscape scale carbon dynamics information. So you can actually get this idea on a very large scale, especially if a forest is disturbed and if you want to map how this forest is recovering from disturbance over large areas, airborne lasers can be a very useful tool for that. Another interesting, I'm very sorry that you don't see the half because of, I used Mac to put my presentation, and when it got transferred to Windows, I think there's a little bit of an issue in formatting. Another really cool way to use data from airborne LiDAR is, imagine that you have collected airborne LiDAR data over the whole of Western Ghats here. And how do you convert this height estimate that you get from this airborne LiDAR data to biomass? So this is one cool way where how airborne LiDAR data can be used. So let's say these little dots that you have are your sampling plots, like your field plots, right? And you know the biomass of the field plots because you've already estimated them from allometric equations. And imagine that you have coincident airborne laser pulses in your field. So you relate the height that you get from airborne laser pulses, and you relate your field-derived biomass. And now you have a model. So if you have a height, then you actually know what approximately your biomass of that area is going to be. And from this simple model relating height and biomass, you can more or less get an estimate of what's the biomass of the region where I collected the airborne data from. So in this case, it's a very hypothetical case. It's very difficult to collect airborne LiDAR data from the whole of Western Ghats. Imagine you have it. You can get this type of estimates from airborne LiDAR. And then came in 2000s satellite lasers. So these lasers also, this is an example, this is a satellite LiDAR called GLASS. So this GLASS was actually put on ISAT, which the ultimate aim of that was to monitor the ice sheets. But scientists started using that LiDAR to actually estimate the carbon in forest. And exactly using the same way, like what I mentioned, relating the height that you derived from the LiDAR to the field-derived biomass, they started estimating the global biomass maps. This was the first time that we started producing maps of global biomass because you had like satellite. Airborne laser scanners are landscape scale, but when you have satellite, you can actually go global. So we started having biomass maps pantropically or globally. But in the second bottom half of the map that you see the uncertainty estimates. So you can get a number, which is like a biomass, let's say 12 megagram carbon per hectare. But how reliable is that 12 megagram carbon? So that's what the second part of the bottom part of the picture showing you. So just to give like one cool thing to look at. So this is like red color means very high biomass areas. And if you look at this color, these high biomass areas are also the regions which have the highest uncertainty. Sometimes the uncertainty of about 50%. So which means if you have an estimate which says like 125 megagram carbon per hectare, it could be anywhere between 50 or 200. And you don't know which of that is true. So one of the major sources of this uncertainty is that you need accurate calibration data set. So how are you deriving your height to biomass model? And because that model is used to estimate your biomass, if your data is really good, you're going to get a better model. But if your data is not that great, you're not going to get a good model. So the sources of uncertainty comes predominantly from your calibration data set. And this simple slide shows you what our calibration data sets are. So your calibration data set, as I mentioned before, you're going to be relating biomass with your DBH with biomass. And how exactly did you arrive at that biomass? So what happened pantropically was they destructively harvested some trees, and they measured the diameter of those trees. And with the destructive harvest data, there is a model which relates these two. And that's the model that we use to infer the biomass of all our plots. Some plots do have site-specific allometric models, which means you have harvested data from the same site to estimate your relation. But in most of the cases, it's not possible. So then what you end up using is a pantropical biomass AGB allometry, which has a lot of issues in itself. But that's the best that you have, and that's what you're going to use. And this pantropical allometry is what these maps are also using to infer their pantropical biometry. So you know that there is an inherent issue in how these calibration data sets are being collected. One of the major issues in these pan-tropical allometry is that they are biased towards smaller trees. You can imagine the size of the tree here. Are we going to cut down a lot of these large trees to estimate this relation? So because of the practical difficulty in getting destructively harvesting a large number of trees, and especially the large trees, most of the time, these data, the calibration data that are used to estimate this relation are biased towards smaller trees. You're going to have a large number of small trees and very few large trees. So there is a bias in the biomass of these large trees. And recent studies also revealed from laser scanning reveals that there's a massive underestimation of biomass even in temperate forests because of the lack of large trees in the data set. So one of the satellite LiDAR data that I showed was from glass, but there are so many other satellite missions coming up to actually estimate biomass of forests, especially tropical forests. One of the missions is JEDI, which is already in the orbit, which is in International Space Station. And there's one more upcoming biomass mission called ESA Biomass, which is from European Space Agency. And India, together in collaboration with NASA, is also launching another satellite called NISAR. And all of these biomass missions actually need reliable calibration data set from the ground. So there was a call from all of these scientists who works on these missions saying like, oh, we need really good data set. If we don't have good data set, we're not going to get a good biomass map, even though we spend millions and millions launching these satellites. And just to give you an idea, why can't we use these airborne LiDAR data to actually estimate good biomass? So in order to estimate good biomass, you need individual level detail. And these 4 pictures are airborne LiDAR data from 4 different tropical forests from Peru, Panama, Madagascar, and Hawaii. And this is the detail that you can get from dense tropical forests, even when you use a very high resolution airborne LiDAR data. So as you can see, you cannot delineate individual trees and you cannot get detail at the level of individual trees. They are very good for landscape scale metrics, but not really good enough for individual level metrics. And then came in 2000s, a lot of different laser. So this laser scanner, which you see here, is called terrestrial LiDAR, because you basically put this LiDAR on a tripod, and then you move the tripod as and when you can scan. This was basically a surveying equipment. This is not really new, that it only came in 2000s. It's been existing and it's being used in civil engineering, for surveying, and for architecture. But in the 2000s, we started adopting it for forestry to see what can we do with this in forest? Can we actually get individual level details from these type of sensors? And then you see the evolution of this being moved on to a backpack or to a handheld, so that you can just walk with this sensor in the forest. You can do transects with the sensor and collect data while you're actually moving. And then even more recent one is this UAV LiDAR. Drones have been in use for a while, but not the LiDAR ones. Mostly you have like camera on these drones or multispectral, hyperspectral. And recently you started having like really high resolution LiDARs on these drones as well. So when I talk about near ground or ground laser scanning, it includes any of these. But most of the examples that I'm going to show is from the static LiDAR, mainly because the other sensors in other platforms, they really do not have the same resolution at this moment as the LiDAR, as the static ground terrestrial LiDAR has. So just so that we're all on the same page, all of these, it doesn't matter which platform you're using it from, they all have the same type of sensor. So, which is like a LiDAR sensor or a laser scanner. It sends out laser pulses, and as soon as the laser pulses hits an object, it's going to be reflected back to the sensor. And based on the time, the total time it takes for the pulses to hit and gets bounced back from the object, that's how we estimate the distance that it hit, the distance of the object from the sensor, and that's how we get the 3D point. And depending on where you put the sensor, the name is quite different. Ultimately, the sensor is similar, the working principle is the same, but based on which platform you're using it from, you either call it terrestrial LiDAR, you call it mobile LiDAR, you call it UAV LiDAR, or airborne or spaceborne LiDAR. And you'll also see that sometimes I use LiDAR or laser scanner, they both exactly mean the same thing. It's TLS. TLS is a nicer way to say it, so we started calling TLS instead of T-LiDAR. And from the next set of slides, I'm going to show you like how different the data quality is across these different platforms. So this is a transect, and this part of the transect is collected from airborne LiDAR, and this part of the transect is collected from UAV, and this part of the transect is collected from static terrestrial LiDAR. And as you can see, this is collected from an open savanna woodland in Australia. This is like a very simple forest. It's not a complicated tropical forest. And even in that dense forest, with an airborne LiDAR, you can get tops 40 points per meter square. Whereas if you use drone or TLS, it becomes better, especially with the TLS, it's like 12,000 points per meter square, sometimes even more. Because this is very simple, you get less number of points, otherwise you're gonna have more points per meter square. And just so that these are all like really good. These are all like Rolls-Royce cars in their own platforms. So these are not like random low resolution scanners. These are all like really the top quality scanners. And this is the best that you can get when you even use the top quality scanners. And now let's move on to a tropical forest. So in an open savanna, it seems like UAV seems to be pretty good than terrestrial LiDAR. So which one do you choose? And if you compare the same UAV scanner and the same TLS in a dense tropical forest, this is the quality of data that you can get from UAV. So you get a lot of hits from the canopy, but as you go to the understory, yeah, can you really delineate individual trees and estimate diameter or other interesting parameters? Probably not, because the data quality really goes down when in a dense tropical forest. And this is the data from TLS. Yes, the density of points is relatively low in the canopy, but you can still estimate really interesting parameters at the branch level, even at the branch level from TLS. Now let's move on to, I'll show an example of MLS. MLS is like mobile laser scanning. And this particular mobile laser scanning was collected from a German forest, a temperate forest, and this was actually operated from a car. So this is a very good top quality mobile laser scanner, which is operated from a car and it's not handheld. And even here, the data quality takes a hit in the canopy, but it seems like it's not doing a bad job in the understory. But this is not a sensor that can be operated in tropical forest, because this is a special sensor which is operated from a car and not in handheld or in backpack. And when you start using a very decent quality mobile laser scanner, which is like either handheld or you put it in a backpack, this is the kind of that you get. This is the kind of data that you mostly get. So there is a huge range limitation. It cannot, the laser pulse, the energy of the laser pulse is not high enough that it can't travel like 100 meters. It's like the tops is like 20, 30 meters. So which means it's not really good in dense forest. You can estimate diameter, but you're probably not gonna be able to do anything better than just getting the diameter. So this is sort of like a summary of these different platforms and in terms of the practical applications. So when you use a TLS, you're probably going to be covering smaller area, but in really high detailed quality. And when you use an ALS, you're going to be covering a larger area, but probably in very low resolution point clouds. And MLS and UAV are somewhere in between. They can really work well for some forests, but maybe not for all. But that's not to say that it's going to be like that forever. Sensors are constantly evolving and developing, and maybe in a few years' time, you're going to have an amazing MLS, which is going to have like really cool range, and you don't have to use TLS anymore. So as I said, this is very good for detailed individual, for landscape scale studies, whereas MLS, at this point, the range is limited, and we can't use it beyond few like attributes in the forest. And ULS, UVLS, especially if you use the top quality one, it can still be pretty good in simple forest, but maybe in complex forest, you're going to get a lot of attenuation in the understory. So in the next set of slides, I'm going to be talking about the really cool ecological questions that can be answered when you have data from a high resolution laser scanner. So I have the picture of a static TLS here, because most of the studies that I'm going to show comes out of the data that's collected from static terrestrial laser scanning. But it's applicable for any type of point clouds that you have. If you have a high resolution point cloud, you can answer all of these questions with that data set. But at this point, only this type of platforms gives you the highest resolution point cloud and not the other ones. So just to give you an idea how the data is being collected. So if you have a tree, you need to collect data from multiple angles of the tree to get a complete 3D picture, because the laser does not penetrate. The laser bounces off. So you need to still collect from multiple angles to get the 3D picture of the tree. And if you collect from enough viewpoints, you're going to get a very high resolution point cloud. This is an individual tree. So essentially what you do in a plot, imagine you have a 50 by 50 meter plot. What we do is we walk with the scanner, we walk with the tripod and the scanner, we move every 10 meters and we collect data from every 10 meters, and then we put them all together to get something like this. So this is a This is how typically it looks when you collect data from tropical forest. And this is a forest in Amazon, and it's a very tall forest. So as you can see, even like 30, 40 meters from the ground, you still can actually get highly detailed data, even the branch level data from such data set. But what was TLS being used, and what's the evolution of this TLS or high resolution laser scanning data in forestry? In the beginning, it was primarily used for inventory purposes. So when you have a high resolution data set, and of course, in 2000s, the data was not as high resolution as this. This is just an example, what was primarily it was used for. Basically, they wanted to get the stem maps of the forest. And from the stem maps, of course, you want to understand what the diameter is. And they were still using allometric equations to get the biomass from these diameters. So ideally, the ultimate aim was to see if we can automate the forest inventory process, if I can just like make it faster to get as much as possible. But in the 2010s, a lot of focus shifted to using TLS to estimate biomass. So what they wanted to see is like, instead of using an allometry, can I just get the allometry or the biomass directly from the LiDAR? Is it possible to do that? And that's what most of the research focused in the first half of 2010. So let's start from there. So you have a high resolution 3D data of a tree. How do you go about estimating the volume or the biomass from the tree? So what you do is you start fitting cylinders from the base of the tree, and you fit it to the point, of course. So you have like a point which look like a cylinder, and you start doing this from the base of the tree to the tip of the tree, and you start doing it the same thing for the branches. And in the end, what you have from a point out of a tree is actually a model of the same tree, and this model is called quantitative structure model. And from this model, what you can estimate is a lot of things, but what it was primarily used for is to estimate the total volume of a tree. And if you have the total volume of the tree, and if you know the density of the tree, you can actually estimate the biomass of the tree. So ultimately, this is your plot level TLS point cloud. What you want is individual trees segmented from this point cloud, which you see here. Each color corresponds to individual tree. And once you have the tree, you actually separate the leafy components from the woody components. And once you have the woody components, you actually fit these quantitative structure models or these cylinder models. And if you have wood density, you get the biomass of the tree. And you do this for all the trees in the plots to get the biomass of the whole plot. And a lot of studies in 2000s have proved that we really get very close estimate to the destructively harvested biomass. So as you can see, the center line, so the x-axis shows the destructively harvested reference biomass. The y-axis shows the biomass from different models. So one is like directly estimated from TLS, which is this red line. And all of the other lines are the pantropical biomass, like Schaaf's pantropical biomass estimates from the allometric equations. As you can see, TLS closely aligns with the reference biomass. Of course, there's a little bit of an overestimation, but one of the cool things is like TLS is like unbiased towards the size of the tree. It doesn't matter if it's a small tree or a massive tree, your error is unbiased, which is what we also want. Whereas from Schaaf, you can see that there is a huge bias when the tree is large, which makes sense because the sample data set doesn't have a lot of large trees. So in the 2000s, there was like a huge evidence showing that TLS is an amazing tool to extract biomass in a non-destructive way. So if you can scan a lot of forests with TLS, you actually have a way of estimating, like establishing new allometric models without having to destructively harvest the trees. So this is so much so that now TLS is actually an integral part of all of these satellite biomass missions. So this is a conceptual figure from JEDI, but this is pretty much the same for the ESA biomass mission and also the NISA biomass mission. They all want TLS to be collected from the small field sites. So if they have like 100 field sites where they are going to be collecting calibration data sets, TLS's data is going to be collected from all of these 100 sites, and they're going to get their plot level biomass estimates from TLS. And this biomass estimate is going to be the basic calibration data set for them to estimate the biomass of the globe or the pantropical biomass. Then the later half of 2010s was like, but this is a volume model of the whole tree. There's a lot of details in this. So we can actually go beyond just estimating the biomass of trees. Biomass is like, oh, carbon is just one aspect of forest. A tree or a forest is much more than the carbon. So in the 2000s, there came a lot of papers using the same data set to address really cool ecological questions. And in the next set of slides, I'm going to show some example case studies which are really cool and which have only been made possible because we have such high resolution data sets. So one of the very recent papers that came last year said like, tree architecture is really important and we are really not using the architectural traits in any of the ecological studies. So for instance, tree architecture is very different, including the leaf and wood architecture as the plant grows. So it's really influenced by ontogeny. And a structure or architecture is directly linked to its function. Imagine if a tree is going to invest in expanding laterally, or am I going to invest a lot in expanding horizontally? So measuring the architecture of a tree says a lot about a strategy of a plant and how it's actually utilizing the resources that it has. And also for reproduction, you need to have a crown structure in order to put your flowers. So a tree's branching structure is going to tell us a lot about its reproductive ability. And also biomechanical stability. How much wind can I actually withstand? A tree's architecture is going to inform us about how susceptible this tree is to damage from storms and wind. And also about hydraulic efficiency. But until now, without the TLS, studying the architecture of trees was actually not that easy, right? So this is a work of Francis Haller. Francis Haller was an ecologist or a botanist really in the 1960s, and he was really fascinated by the architecture of trees, and he literally drew this. So this is actually his drawings of how a forest looks like in French Guiana in Nurag. So this is how he visualized the forest. So basically he drew, it's a schematic diagram that he drew. Of course, not every one of us are a good artist like him, so we cannot do this, and it's not a scalable technique. You can't go and draw such an architecture of all the forests. But TLS actually provides us an amazing way to understand the detailed architecture of the trees. So for instance, again, if you have the tree, this is the data from a TLS, and if you have such a data, yes, you can estimate diameter at breast height, you can estimate the total height of the tree, simple parameters. And in case you have a buttressed tree, you can actually estimate the diameter above the buttress, which is still a huge challenge in a lot of tropical forests, where sometimes the diameter above buttress is like 4 meters, 5 meters, or even like 10 meters from the ground. And people still use a ladder to climb on the tree, climb to estimate the biomass above the buttress, diameter above the buttress. And TLS can be an amazing tool to make it easy, let's say, or less dangerous to estimate the diameter, to get reliable estimates of diameter above the buttress. And once you have this, you can also estimate the crown projection area, how big my crown is. And you can also get the crown volume. This is basically the overall crown volume, including the foliage. And then once you have stripped off the leaves and you have this quantitative structure models, the list is endless. You can actually extract a whole suite of parameters. You can know what's the branching order. So the color here corresponds to the different branching order. So the main blue one represents the trunk of the tree. And every time a tree branch, you have like green color responds to the first order branches, the red color corresponds to the second order branches, and so on. So you can know the branching order of a tree. You can estimate what's the parent branch for this particular daughter branch, and what's the angle between these branches, and what's the length of the branch, what's the surface area of the branch. And these are just some examples. What's the crown depth? What's the crown volume? So many other parameters. You name it and you can have it. So it's like endless opportunities to measure very detailed attributes of a tree. And now I'm going to show you some examples of how this data has helped us understand some of the questions. So one of the first thing I'm going to show you is about like wind damage. So a recent study, not so recent, like 5 years ago, by using like TLS data from a variety of forests, from temperate to tropical, they showed that architecture of the tree has a huge influence on how susceptible is a tree to wind. So basically, slenderness is commonly used. So how tall the tree is with respect to ratio of height to the diameter is commonly used as a predictor to assess the susceptibility of wind damage for a tree. But they showed that instead of just using like height and diameter, if we use the architecture of the tree, we are able to predict the susceptibility of the trees to wind damage better. And another interesting paper showed that we can actually start testing really cool ecological theories. So metabolic scaling theory, one of the propositions of metabolic scaling theory as a tree, if it has a symmetrical structure like this, it has the best, it can utilize its resources at the maximum when it has a very symmetrical structure. But of course, we know that it cannot happen in reality. But now we can actually start testing like how far away from theory I am and why am I this far away from theory if symmetry is what is going to give me the best, if that's how I can maximize my resources and carbon gain is the maximum and I have symmetrical structure, why am I not symmetric? You can start understanding these questions with this data set because you have branch level detail to test these theories. Another interesting aspect is to see how climate change and anthropogenic disturbances is actually affecting our forest structure. So this study actually collected TLS data from edges to the interior of the forest. So all of these edges are basically forest fragments, right? They have been cut for agriculture or for other reasons. And they showed that the edge trees have a very different architecture to the trees in the interior, so much so that it resulted in massive carbon losses. So basically, what we do is we use the same allometric equation. If you're estimating the carbon of a forest patch, you're going to be using the same allometric equation. But they show that if you use the same allometric equation, you're actually overestimating the carbon of these forest fragments, which is a problem because you don't want to have a lot of forest fragments, especially in forests like Amazon, which is supposed to be a continuous forest. So they showed that using different allometric equations actually explains how much carbon is actually lost from these anthropogenic disturbances. And another really cool paper, which actually came out a couple of months ago, which showed that, oh, wait, trees are not just good for carbon uptake. They also actually uptake methane. So what happens is like microbial activities in the bark of the tree actually absorbs methane from the atmosphere. So how did TLS contribute to this study? So since it's the bark surface, you want to know the surface area of the tree. And it's very difficult to estimate the surface area of the tree because it's not possible to estimate. But there are some allometric equations which relate the diameter to the surface area of the tree, which again was established from a very small data set, and it has a lot of uncertainty around it. So what they did was they used TLS. And since I already showed, TLS is basically made up of multiple cylinders. So if you know how to estimate the surface area of the cylinder, you can actually estimate the surface area of the whole tree. So they developed new models which relates the diameter to the surface area of the tree. And they used the models that was developed from these TLS data across a very wide range of forest types to show that how much methane can forests uptake. And another cool thing, so this is basically one of my PhD work. So what we did was we scanned a 50-hectare area in BCI. Of course, we didn't scan the whole 50 hectare. We scanned a 4-hectare area in BCI. And what we did was we wanted to understand lianas, which are climbing plants. So they use for trees as a structural support to get to the top of the canopy. So by doing so, they have a huge impact on the reproductive ability of the trees, carbon uptake of the trees, and overall the structure and functioning of the trees. So we wanted to understand how exactly lianas are having an impact on tree structure and function. So we collected data from a 4-hectare area, and we looked at trees that have no lianas, and the trees that have like 0 to 50% of their crown had lianas, and trees that have like fully loaded with lianas, which basically have lianas all over their crown. So what we found out was the total architecture of the trees were completely different. So it's hard to say if they are different because lianas prefer certain architecture to infest, or if they are different because lianas infested them. But what we observed was the trees with lianas had like very low crown volume. Their crown area was significantly smaller, like about 30–40% smaller, and their crown length was also really shorter. And not just this, we even observed details at the level of branches. So trees with lianas had like really small surface area, and they also had like shorter branches, and overall branch numbers were significantly lower. This could be because the trees are not photosynthesizing, so they stopped dropping branches as a way to shed lianas. This is a possibility. That's why you see less number of branches in liana-infested trees. We don't know why exactly this is happening, but we do see a massive difference in how trees look when they have lianas and when they don't have lianas, and which is going to affect the functioning of the trees. And when I arrived here this morning, Surya mentioned that there's a lot of interest in mangroves, and there was a question like, can we actually use, it was not a question, but I also wanted to show that TLS can be used in mangroves, and mangroves are not really easy to penetrate. And people actually have scanned mangroves with TLS, and it has really provided cool insights into the root biomass and the structure of the mangroves as well. And as I showed some of the examples, these are only touching the surface of what's possible with the LiDAR. with the high resolution data set. So one of the things I mentioned is like how architecture is linked to mechanical stability, hydraulic conductivity, carbon sequestration, and also heat protection. But we have a lot of data, but we haven't actually tested any of these theories. So one of the hypotheses is that a tree which has an umbrella-shaped branch, it's going to be really good at intercepting light and therefore carbon capture, but it's going to be hydraulically inefficient because it's going to have a huge, so the water from the root has to reach all the leaves until the tips. So if you have like a really umbrella-shaped structure, you're going to have a lower hydraulic conductivity because the water is going to have the same path length to reach all the tips of the leaves. Whereas if you have a lower path fraction, you're going to be better at hydraulic conductivity, but probably not so good at light interception and carbon capture. This again, architecture can actually bring us really new insights into different strategies that the plants are adopting in the forest. And this can also help us understand how climate change, which is changing all these, some forests are becoming drier, some are becoming wetter, and this can give us really cool insights into which plants will be able to adopt better to these conditions. And one of the things that I want to mention is it's not just you have to study trees. You can also study a lot of other plant forms. So as I said, one of the things that I was fascinated about was lianas. So on the left-hand side, you see a picture of a liana. So what happens when normally inventory, lianas are never a part of the inventory because either they never make the cutoff because the basic cutoff mostly people use is 10 centimeter and most of the lianas are less than 10 centimeter. You have very few lianas that exceed the 10 centimeter cutoff. So they are never a part of the inventory. And therefore, the way we estimate liana biomass is like really uncertain because there are some destructively harvested lianas, but if for trees, the total number of destructively harvested trees to estimate, to establish the allometry was 5,000, for lianas, it's a mere 300. So of course, the biomass is going to be very uncertain when you use that. So what I did was like, we tried to see, can we use TLS to actually estimate liana biomass? And if so, we can also avoid using destructive methods and establish new allometric models from TLS. And we basically delineated lianas from these scans, and we got all the lianas, and we measured the biomass of the lianas using a very similar but a slightly altered quantitative structure modeling approach. And again, it's not just woody structure. We can also really do cool things related to the leaves. Because we are segmenting the leaves from the woody components, we can start measuring a lot of interesting things like what's the orientation of these leaves. We know leaf orientation is really important because a horizontal leaf is going to have a lot of light interception, whereas a vertical leaf is going to have lower light interception and so on. And it really, and we know like plants adopt these things. And it also, again, informs us about the plant strategies. So we can start looking at all of these cool things related to leaves, which is a crucial modeling parameter as well. And right now we use a mean value for all the species, and every species have their own leaf orientation. And we can use TLS data to estimate leaf angle distributions to inform the model better. Then again, TLS is not just for individual level metrics. We can also actually estimate like do plot level studies. For instance, what you see here is to analyzing the forest succession in Gabon. How does the vertical structure of the forest changes as the forest grows from monodominant forest to mixed forest? How does it look? So as you can see, you can check how complex a forest structure is. For instance, a colonizing forest or a new forest is like, it's very short, but it has a lot of understory, as opposed to a mixed forest, which is going to have a bimodal peak. It has a lot of understory, and it also has a very complicated canopy. So you can get a lot of plot level insights. You can monitor forest, degraded forests and how they are recovering. You can do a lot of cool plot level studies as well with TLS. Having said all the cool things that you can do with TLS, I also want to end the talk with saying there are also challenges. First, I want to mention this. The time and cost is a major limiting factor. What you see here is 4 different terrestrial lidars. So you can see the tripods there. So these are all like terrestrial lidars. And this is the cheapest one that's available in the market. And you can see the range is very limited. It's a 60-meter range. And this already costs about $25,000 US. And the most expensive one in the market, which is like the Rolls-Royce of terrestrial lidar, is this Regal one. And you can see the cost is like $120,000 US. So it's not a cheap equipment. It's still a very expensive equipment. And you can use like our BLK, but it's going to have a lower resolution, and it's going to have, it's going to attenuate in the canopy. So you might not get a lot of signals from the canopy. So again, depends on the topic of the project, and it depends on a lot of other factors like budget, but purchasing or owning an equipment is not that easy. It's quite an expensive equipment to own. The second part I want to say is like data collection is easy, but processing is really hard. So what I showed was all the process data set, but a lot of time goes into actually getting all these individual trees out of the data. So ideally what we want is, this black is a plot level data, and we want individual trees like these red things very beautifully extracted from the data set. But in most of the cases, the algorithms that exist as of now will give you, this is even the best case scenario, will give you something like this. We'll give everything together as one tree, and someone has to sit in front of the computer and manually clean these trees to get the individual level data. So we are not there yet where you can just collect your data, put it in the software, and expect the individual trees out. No, we are not there yet. The individual tree extract segmentation is still a challenging step, and we are working on it, but it's not there yet. The same goes with leaf wood separation. Yes, there are algorithms that could separate leafy components from woody components, but again, it's going to have a lot of misclassified points, and we are not there yet to just make it operational and ready to go. But of late, we are seeing a lot of new deep learning based methods. Deep learning requires a lot of data. So right now we have a lot of data, and people are working together, contributing and sharing data with each other. And all of these data are going into developing better models. So in the future, we are going to have a much better model, and we are going to have a software which is like you plug your data in and you get the individual level metrics extracted. But then again, it's few years down the lane, or maybe even months. I don't know how fast these things are developing at right now, but as of now, that's not the case. The second thing, occlusion. So what do I say when it's occlusion? In a dense canopy, even though your LiDAR can actually go to 100, 600 meters, you're still in a very dense area. You have a lot of objects around you, and the LiDARs don't penetrate. So the number of pulses that even reach the canopy will be a lot less in a very dense forest. So you still get returns from all of these areas, but the number of returns is going to be way less. So even the best one that you have in the market is still going to suffer from occlusion, and you cannot expect the same quality of data that you have in the understory in the canopy. But there are ways in which you can minimize it when you are acquiring the data. So here you see 3 different types of protocols. In the first section, you see like you're collecting data from every 30 meters. And in the second thing, you're collecting data from every 20 meters. And when you go and collect data from every 10 meters, you start seeing that the quality of the data significantly improves. So by collecting or by increasing the viewpoints, by increasing the number of viewpoints from which you look at the tree, you can actually minimize the occlusion. This is exactly what people do when they're measuring height from the field. If you just constantly look at one way, you're probably not going to hit the top of the tree. But if you keep moving around the tree, you will always have a spot where you get the best view of the top of the tree. And that's exactly what you do with the LiDAR. You're going to have to collect from as many viewpoints as possible, and you can minimize the occlusion by improving your data acquisition protocols. Another way to go about is if you have a UAV LiDAR data, if you're so rich and you have multiple sensors, super expensive sensors, and you have UAV and you have TLS, you can fuse them both. And then you can minimize the occlusion to a greater extent as well. And here is an example which shows the top areas densely covered just by fusing these 2 data sets. So why is the data quality so important? And why do you have to make sure that you have a good acquisition protocol? The QSM, which is the cylinder fitting model, can only be as good as your data. If you have a poor quality data, your QSM is going to look like this, which does not make any sense here because it's just fitting some cylinders to your points. If your points are missing, if your points are noisy, you're going to have a noisy QSM. So you need to make sure that your quality of data is pretty good to have a good quality QSM. So there has to be some quality control to which trees are you going to use to do this in-depth investigation. But again, AI is also doing a great job there in the sense if you have a lot of missing areas, a reasoned algorithm is actually filling your gaps for you. So if you have a gap, so for instance, there is a gap here, and AI has actually filled the gap. So this is very preliminary. It's not there yet, but it looks really promising. So eventually in future, if there are gaps in your algorithm, you probably can have AI which actually fills the gap for you, and you can still use those data sets. So again, summarize, TLS is definitely revolutionizing the field of ecology. We are able to answer so many cool questions because we have such high resolution and detailed data set. And this has become like the fundamental building blocks for all these high, like satellite missions or biomass missions. And TLS is like creating the validation data sets for all these upscaling techniques. But is it an off-the-shelf solution? No, we're not there yet. We are working on standardizing the protocols. We're not there yet that you can just use it and get ecological questions answered. There is still a lot of processing behind that goes on. And is it a holy grail for all ecological questions? Again, no. It gives you a highly detailed point cloud, but it's still going to be small scale. Unless you have this off-the-shelf solution, we cannot collect data from really large areas and answer these large, like process all of these data. Once we have everything set up, maybe you can collect from larger areas, but it's still going to be, you still need to integrate it with other remote sensing questions to get a bigger picture. It's still going to be a very small scale, highly detailed study. And with that, I would like to thank all my collaborators and people who helped me with data collection and everything. And I'm open for questions. Thank you.
Dr. Sruthi. It was nice going through the whole evolution of the technology. And also what was more important was you explained now the possibilities and also the limitations. So thank you very much for that. I hope you take a few questions, right?
Yeah. I'm open for questions.
And once again, welcome to the students from Foster College. Yes. So the floor is open for questions.
Shruti, I have this question.
Yeah.
That, when it comes to the canopy,
Can you switch on the mic?
when it comes to the canopy,
Yeah.
one possible thing is its movement. So,
Yeah.
how often it is there?
So we try to collect data when it's not windy. So that's one important thing. So make sure that the wind is less than 5 meters per second speed. That's what we keep as the cutoff. So as long as the leaves are moving, it's still okay, because that's impossible to get that level of detail. But we do make sure that the branches don't move, because then you're going to have like a misalignment error and you're going to be overestimating, or you have to do a lot of manual cleanup. So yeah, wind is a major factor, and also rain, because you're going to have a noisy returns from the rain. So during wind and rain, we normally don't collect data. So we also pick a season when it's the least windy when we go to the field. And if there is a gust of wind, we don't scan them. Yeah, that's an issue, yes.
Thanks for the presentation. We have quoted a paper
Mm-hmm.
on the impact of liana on dam protection.
Yeah.
And how does it, whether it's a, based on the data, whether it's a species-specific phenomenon?
So,
For example,
Yeah. I will go back to that.
I mean, both the host and liana.
mm-hmm. So there are two different things. So what we see in the field is like lianas are not present in all the species. There are some species which do not have any lianas at all. And there are species which have a lot of lianas. But here we compare the species that has the liana. So in the species, when they have the liana, species is always included in the model as an effect. And this is predominantly present across all the species. Once they get infested by the lianas, they do have like they are shorter, they seem to be somehow not investing in their crown biomass because they are shaded by the lianas. And you see the most effect in this scenario when the lianas are fully occupying the crown. But the thing is, how many species have lianas, so much lianas in their crown? Not a lot of species. I think some species are very good at getting rid of lianas earlier. Or one other thing is also there are some species which just die when they have lianas. Like, for instance, early successional species, they seem to have a very high mortality rate when they get infested by lianas. So it's hard to say if they are, normally they don't have a lot of lianas when we go into the field, but it's not because they are very good at not having them. It's just because they die faster when they have lianas. So you don't really see a lot of species in the early successional stages with the lianas, but the driving factor for that is sometimes a bit different. So in this study, we only look at the species that has the lianas in them, and then we compare within those species the individuals that have lianas and that they don't have lianas, and then we see that there is a huge difference in the architecture of those individuals within the same species as well.
Is there, when you look at the impact of multiple species, multiple liana species on a single tree?
Lianas, okay. We didn't really look at the liana species at all.
Oh.
It doesn't matter which lianas, as long as there's a liana in the tree. Yeah, sorry, if it's a liana species, no. We didn't really look at the liana species. All the lianas are just grouped as one. Of course, depending on the climbing strategy and everything, there is a huge difference in how they impact the tree, but we actually did not look at the liana species here. Yeah, only the tree species.
Can lasers curve?
You mean like, can they go like this? Normally, there will be like an energy that gets like bounced off when it gets reflected off the object, but they are highly collimated beams, so they just travel straight to the object. When they return, it's possible that they get diffracted, but the lasers only can, so it has to get reflected back to the laser to estimate the distance. So if something gets like distracted, no.
You mean to say that if we want to get a clear picture of one tree, then put this.
Oh yeah, but we move the LiDAR itself.
Okay, fine.
Yeah.
But still, one very fundamental question.
Yeah.
There's a laser beam going.
Yeah.
And there will be different time points at which the individual laser particles are moving.
Mm-hmm.
And how does the machine understand that which particle is coming back?
So it's not exactly sent at the same time, right? So it's always sent at a slightly different time. And it's also like they all have wait. I have to go to the airborne laser scanning thing just to show you like. So what they sent out is like a pulse with this intensity. So this is what is actually going out. Can you see this is what is actually going out. And the whole of this is what is actually returned. And every pulse is actually sent at a slightly different time. They're all not sent at the same time. So you also have like a timestamp to all of these pulses.
Yeah, timestamp is fine, but then by progress, I have a machine over here. The laser beams are coming. It strikes the first person over here, it comes fast.
Yeah.
Second person comes a bit later. But the last person, it comes very late.
So a single laser beam, when it travels back, what is traveled back is actually the whole pulse as such, not the individual returns. So what happens later on is you discretize them based on the amplitude. So when you see like the first return, so what you see here, the first return, second return, and the third return, this happens later. This happens after. So once it gets the return, it's discretized later on. So what you get is actually a waveform, and the waveform gets discretized. And sometimes some companies provide the waveform itself, but a lot of other companies only provide us the discrete returns. But technically, it's all processed in waveforms, and the discretization is done once it's returned within the LiDAR itself.
It's basically a cloud which is issuing.
It's a light pulse,
okay,
in the form of a wave. So a wave is sent and a wave is returned back.
What is the status of the allometric equations for different species? Do we have very strong allometric equations for all different species which will help us calculate the biomass?
Well, it really depends. I think forest ecologists here can answer the questions better. But in most of the cases, there are some field sites which have established their own site-specific allometric equations where they probably focused on important species. But most of the time, species information is never in your allometric model. What is in your allometric model is mostly wood density, which is like fundamental parameter in your allometric model, and a very broad term, especially in Sharp's equation, which is the most commonly used pantropical equation, you're going to have like a broad term which actually talks about the environmental gradient, what type of environment you live in, which affects your allometric equations as well. So species in a pantropical allometric equation it's not there. But maybe if you have a site-specific allometric equation where you have established your own allometry for those species, it might exist. But I still think it's not that common to have site-specific allometric equation.
Mainly for commercial species.
Yeah.
And even for some endemic species, there's literature we have.
Okay.
And there is a collection, equations collection from FAO, which compiles the all species level information databases.
Interestingly, this place, they have an agriculture university here, the students are from Foster College. They have a veterinary college over here. And it was the professor in veterinary college who prepared the first allometric equation to calculate the surface area of the elephant.
Oh, yeah.
So that is a very interesting book, and almost a decade. So
Yeah.
we made an equation. So
Allometric equation is a very broad term.
Yeah.
For all the animals, you use the same to estimate their mass versus surface area and everything. Yeah.
one question which you have to address is the identity of the species.
Yeah.
So are the AI models ready enough to identify the species from the
I think I have an extra slide which shows exactly this question. So I didn't talk about it in the presentation, but I did have some slides. Was expecting like maybe there's a question about species. In tropics, it's pretty hard because yeah, you have so many species in a very small area. Because again, if you want to automatically identify species from data, either you can look at the data and you can look at the structure and you can tell them, but I think most of the time people identify the species from their flowers or their leaf shape or their fruits rather than just with the woody structure. So I think there's a bit of a limitation there because it's very hard to still identify the whole leaf shape very clearly from LiDAR. And again, you need to collect exactly at the same time when it's flowering or fruiting. I think it's pretty difficult to just use LiDAR data to do that. But I think multispectral data, if you can fuse the data with multispectral images, there is a possibility, but I think it's still pretty difficult to identify all the species in the field, and we still need field experts or taxonomists to help us identify that at this point. So some work has been done in temperate forests. That's what one of this work. So they were able to identify and delineate very easily between these 6 species, but all of these species identification work comes from temperate areas or areas where there is limited number of species that exist. There, it's a possibility.
most of the data in forestry is skewed towards the temperate forests.
Yeah.
We don't have enough data in the tropics. So when you compare, when you extrapolate, is going to be huge error happen. One other question is regarding one of the slides you showed in which there's a laser beam coming from top, and it is getting.
Yeah, that's one thing I said. Yeah, it's going to. So there is a term called beam divergence. So your beam is always going to diverge.
Why is it because of scattering?
So that's the basic principle of light. So when a light is sent, the energy is super high, so it's going to be collimated. But as soon as like it's reaching the ground, it's going to like delineate. But the delineation, how much it diverges, depends on the distance that it's traveling. Like longer it travels, more divergence you're going to have, and it also depends on the energy of the laser pulse and everything. So that's the That's how fundamentally light travels. So you're going to have. This is always going to happen.
So it is not scattering, it is just entropy.
Yeah, this is not scattering. This is how it's like falling on the object. So that's also why, depending on the footprint of the LiDAR, the size of the object, the smallest size of the object that you can measure changes. So in an airborne LiDAR, the footprint size, when it falls on the ground or the object, it's going to be maybe 3 meters in a very good airborne LiDAR, could be 10 meters in a like reasonably, or not even a low resolution LiDAR. If a LiDAR is operating from a much higher like distance, higher altitude, you're going to have a larger diameter on the beam, because sometimes the altitude is designed based on the aircraft that it's used to fly upon. So if you have a certain type of aircraft, you have like a limitation, country limitation. You can't sometimes fly below this height. So depending on the altitude that you're flying, the footprint, the LiDAR and the altitude, the footprint is going to be different. So larger the footprint, bigger the size of the object that you can actually like discriminate, let's say. So in airborne LiDAR, that's also why if it's a 2 meter, 3 meter airborne LiDAR, if you have a whole tree, you can maybe get few points from the tree, but it'll never be good enough to identify that it's a tree in sometimes, or like the shape of the tree or something. Whereas in terrestrial LiDAR, because it's actually operating on the ground, this divergence is always very, very minimal. So basically it's few millimeters or centimeters. So you can even identify branch level detail because of that, because the beam divergence is very low here. Yeah, but the divergence exists in all the platforms.
You showed a aerial photograph in one of the first slides. Yeah. So I think there are at least a few in this room who have started our work using aerial photographs. Maybe it's Rajit, myself. So at that point of time, the remote sensing data was not at all available.
Yeah.
We were working on photographs, and when we put the side-by-side photographs under the stereoscope, at one point they matches, and we see the elevation model. You can
The
see the
digital
mountains coming up, the values going down.
Yeah.
And personally, there is a bliss. There is a wonderful feel as if you're flying on a aircraft looking down. You can see the mountains coming up. I have never ever enjoyed that sort of moment with the remote sensing data, because it is not just digital. It doesn't get a feel of the landscape. So when you are able to look at it with our eyes, there's a large amount of interpretations which are possible, especially when you know the landscape. Like for example, this picture, if you have walked through the area,
then you know better.
You can add a large amount of information. Are aerial photographs still in the game?
Well, one of the things that with aerial photographs are amazing is like, because they all exist pre-1960s and 1950s. So one thing that one of our colleagues is trying to do from Oxford is like, they took these aerial photographs, and also not just aerial photographs, really the maps from archives, and trying to really understand how the landscape has changed. So that's something that we are actively working on, using AI again in trying to understand. For instance, if you want to know the depth and the actual height, it's still pretty difficult to say the height, right? Because you can infer it a little bit. Relatively, you can say, okay, this is ground, and relatively, I'm a bit higher up the ground, but you still cannot say with certainty how much higher you are. You can just only, from photographs, if you don't have like multiple photographs stitched together, which is like a stereo image, inferring depth information is still pretty difficult. Some algorithms exist, but they still give you the relative picture. But one of the cool things that they are using this to see how landscape, because we don't have any remote sensing before, Landsat was like the first thing that started to come up in 1980s. But pre-1980s, we don't have a good record of how forest cover existed and how that changed. So aerial photographs and also archived maps, basically like also all the British colonies, they have maps in the archives. So that's now being used to understand, especially in the colonies, how the forest landscape has changed from the pre-colonial to now. So yes, these photographs are like really amazing, and they give us a wonderful picture, as you say, about the landscape and all of these things. But in my opinion, inferring, you can estimate forest cover, and you can estimate a lot of interesting things from it. But I think getting height and these kind of things is very difficult. That's what I mentioned. But these are really cool tools to understand the history and all of those things.
Last question from me. You can estimate the volume of a tree using this particular technology. I'm asking whether a situation where you have a mined area, a granite quarry, can you use this technology to estimate the amount of rock which has been excavated from this?
Well, technically, the LiDAR that we use, like the one that you see in this picture, not this one, the most expensive one, it's actually used in mining areas.
Okay.
One of their major purchases or major clients are actually land mining companies. And next is architecture, but mining is their ultimate clientele. We are basically like nobody for them because we are not the ones with the most budget. Mining companies are the ones that buys these kind of, especially the high resolution one. Mining companies are their clientele. So yes, it's being really used for exactly these purposes in mining and in architecture as well.
Yeah. Recently, there was an attempt in Kerala itself using the aerial LiDAR scanner, terrestrial LiDAR scanner, and bathymetric LiDAR scanner for estimating the volume of rock extracted from a mine. Why?
Is it published?
It's not published. It was a
Will the
group of
publish?
people come together to do an exercise just to estimate the land. For second. It was
Last
published.
Friday.
Should be one last question from my side.
Yeah.
Maybe I am a new man for this area. Very primitive information only I am having.
Yeah.
So I'm just thinking, you using laser from this aerial thing, I can understand to limit the interferences and all. But when it comes to a tropical evergreen forest, where even 20 meters is an luxury, you won't get that much space. Why can't you use pixel? It's conventional instead of laser.
So all of these are multi-return LiDARs, at least the ones that you see. So with the pixel, you cannot really get the height of, you can just, hemispherical cameras does give you like gap information, but you cannot still estimate the detailed metrics. Like, can you estimate height from pixels? Probably not. So if you have a picture, and if you have a mic here, if you have like someone sitting here, picture is just going to give you an overall information. Just from looking at the size, maybe you can say you're sitting behind her, but you cannot really say how far you're sitting behind her, right? Can you say like, oh, I'm like 5 meters from behind her? No, that's information is very difficult to get. So these active remote sensing technique actually gives you just the distance. It gives you very detailed information about everything that you want to measure. And it also is multi-return, which means when I send a pulse here, and because of the case that you have a beam divergence, only half of the beam is going here. Rest of the half of the beam actually goes behind what's here. So you get actually even 10, 15 returns from just one light. So you're actually seeing behind what's this object. So you're actually getting a very detailed photograph, because it's not just once you get a return, it's not that there's no, that you have to collect again from that side. No, these LiDARs are multi-return LiDARs. So every time you send a pulse, the energy is still sent further, and you get returns from even like, that's why you get returns from even 100 meters. And you say like there is no visibility, so what's the point in using it? It's not like it's not visible at all. There are always like gaps. And I have been amazed that I wouldn't be able to see what exists behind it. But if you look at the data, you can still see that the LiDAR is able to. So what happens is like we put a lot of reflective control points, because we are collecting data from multiple places, we need to put them all together. And we need to have like common points to say like, how do I put this one and this one together? So what we do is we place some manual objects in the forest, which are used as the reference. Sometimes in the forest, what happens is like, I wouldn't be able to see a particular manual object that I put in from one position, but the LiDAR will be able to see, because these are really thin collimated beams, and they can really pass through very, very tiny gaps, which we miss sometimes. So no, they are not really a replacement for like pixel or optical imagery. They can be used complementarily, especially in case of like if you want to like distinguish leaf and wood. Yes, optical imagery can be used complementary to it, but you can't get the same details. You can't measure volume, or you cannot measure height, etc., just from optical imagery. So I think it's a very different purpose of what you want to use the sensor for. Yeah, if you're not interested in individual level details, yeah, you don't have to use the LiDAR. You can use optical imagery as well.
My question was like whether it is the property of the detector or the light itself, because the detector,
Which is the like the
so the visible light, if it is coming,
Mhm.
we are using such a kind of technology to measure the distance as well between the
So the difference is this: optical imagery uses the visible light, right? So it's passive. So basically the sunlight, that's what optical measure, that's what you see. Whereas in LiDAR, the difference is you're not using the visible light, you're using your own light. So normally what you use is a near infrared beam. So the beam is not in the visible range. The beam is normally 1,550 or something like that, or 900, based on different LiDARs have their own beam. So you're not actually measuring how a object is reflecting the visible light. You're actually sending your own pulse, and you're measuring the reflectance of that pulse. So fundamentally, they operate slightly differently. So that's why what you can measure is also pretty different in these two techniques. Yeah.
And the LiDAR films create a shadow.
The shadow would basically be what we call occlusion. So if you have a massive tree, the beams don't penetrate beyond the tree. So whatever is behind the tree will not be captured because it's a massive tree. So then that's why we also collect data from that side so that we get those objects covered as well. So there's no shadow, but what you call as shadow is like the occlusion. If you have a massive object, because you don't penetrate, you're not going to get anything behind it if you scan from one position. So that's why we scan from multiple positions.
Does the occlusion have the same surface features like the tree?
Yeah, it will look, so you can clearly see in the data that you have missed everything that's beyond the tree, behind the tree. So you can see from the data that this is the tree that has caused the occlusion. Yeah, that's possible. That's clearly visible. Yeah.
And for a nice lecture, I have two questions.
Yeah.
Small questions. Can we determine the health of a particular tree or health of forest through this imaging system?
So,
And second question.
Yeah.
Second question, whether this tool is only useful for above ground or it's also useful for below ground?
so the first question, health of the forest. It depends on how you define the health of the forest. So if your health of the forest, by health of the forest, you mean you define based on the wilting of the leaves or things, it will be pretty difficult to do it because it's not going to give you the chemical properties of the leaves and stuff. But if you want to identify if a particular forest is degraded from the structure, because that you can say, because if a monodominant or a forest that's just starting to secondary forest is going to have a very different vertical structure from a primary forest. So if by health of the forest, if you mean if a forest is like massively logged, or if a forest has caused storm damage, if you want to detect that kind of health in terms of structure, yes, you can do it. And people are using this to monitor the recovery of forests following a disturbance like storms and drought and stuff. So that you can do. But it's still, yeah, how you define health depends on that
Suppose
purpose.
if any pest and disease attacks on particular tree or some area, the all trees are damaging.
Yeah, then you can, of course, you can see it. But then I think I would still say aerial LiDAR would be a good idea to have where this has happened, because this is an equipment which you still have to carry. So you still have to know there has been a damage in this area, and then you go with the equipment to that area, and then you make the analysis. I think remote sensing can give you, like the satellite remote sensing can already give you a sense of what has happened. And maybe once you know this area has been damaged, then you can take the LiDAR there, and then probably you can get an estimate of how much damage has been there. So I think this is very good to actually quantify the damage rather than to just detect the damage. I think for detecting, there are other really cool techniques to do that. But if you really want to have a number to quantify, I think this is one of the best ways to do it. But you need to have like temporal, right? You need to have a data before the damage, and then you need to have a data after the damage to quantify. That's one thing. The second question was about the below ground. As I said, it does not penetrate.
Yes.
So you're never going to get anything below ground unless you excavate the ground, and then you can see the tree like with your eyes. Then you can measure the roots with this. But no, it doesn't penetrate. It just bounces off the ground. So yeah, it's not good for people. Use like other ultrasound techniques for I think roots and stuff, and not the LiDAR or radar techniques.
Is the data available for purchase? Is just like remote sensing data? Can we purchase the data?
So it's still a very scientific. So we still don't have a lot of. There are a couple of commercial companies which actually start to use LiDAR for forestry, but it's still a very much an academic, academic project, let's say. So most of the data is available open source. So
Most satellites might come up.
oh, the satellite. JEDI is already available, and it's like open source, easy to use. Biomass, I think it's launched, but we still haven't seen the data from it. But it's also open source. So you can, all these satellite biomass data, you can download them for free.
So what is the frequency?
The frequency, JEDI is like pretty difficult to say because it's on the International Space Station. So JEDI collects data wherever International Space Station is moving. So
International Space Station.
Yeah, you can get all the geo coordinates and everything, but the frequency is arbitrary. It's not like it's going to collect the same area few times. Like Sentinel, you know the frequency. It's like every 3 days, every 4 days. But with JEDI, sometimes you can actually get the hit in exactly the same spot multiple times, but sometimes you only have one hit from exactly the same spot. because Jedi is not on a satellite, so they don't determine how frequent they can actually collect data with Jedi. Jedi is just on an International Space Station, so it all depends on Houston and where they decide to fly. So some areas are covered really a lot because that actually falls within the, let's say, like how the orbit of the ISIS. So there you have a lot of data, but in other areas it's quite sparse.
But this new satellite is going to come up with a project of ISRO, NASA
Yeah,
combination.
Nisar.
Is it going to be geostationary?
I think that's going to be a satellite. So I still don't know the frequency, but it will be definitely a wall-to-wall mapping compared to the Jedi. But off the top of my head, I don't know the frequency. But I know it's more than few times because the idea is also to map the recovery and dynamics and stuff. So I'm sure it's more. And for biomass is also going to be frequent, but that's a radar or not. And both are radar and not LiDAR, but they are going to be much more frequent than Jedi. But Jedi is already available and it's free to download. I don't know about Nisar, but biomass will be also freely available to download.
The satellite radars penetrate the cloud.
They do. This LiDAR, it gets like less affected from the cloud. Also radar, probably not, it's not optical. Optical is the ones that's most affected from the cloud. But the problem with the radar is they saturate because of the wavelength is much larger, right? So they tend to saturate in very dense canopies. But I think the type of radar technology that they are using, especially in Nisar, is meant, not in Nisar, in biomass, is meant to penetrate denser canopies because the wavelength is like much shorter and it's not the usual L band, it's going to be P band. This is the first time that they are launching P band. So they are expecting pretty good returns from dense tropical forest as well. But I think we still haven't seen the data yet.
The normal most our major problem is the cloud.
Yeah, cloud cover.
So this can solve it.
Yeah, the probably energy attenuates a bit, but they have less influence because in optical, if you have a cloud, you don't see anything behind it. But these are less affected by cloud problems. So that's why they are much more, so you don't have to, if the data is available from that location, it's probably of a decent quality because it doesn't have like influence from the cloud. Yeah. Yeah.
Very nice presentation. You know, in one of your slides, you told about uncertainty.
Yeah.
Like, what's the statistical logic behind estimating that uncertainty map of any biomass area?
So you have to propagate the uncertainty because the uncertainty comes basically from your field estimates, right? Yeah, here. So the uncertainty is basically propagated at multiple levels. I did not develop those models. So I don't really know exactly how it's done, but I know how they did it for Jedi. So what they do is you have field data, and technically when you have like a LiDAR that coincides in your field, so you estimate your attributes from LiDAR, let's say height, and then you have your field biomass. But the biomass itself has an uncertainty estimator because you are using an allometric equation, and that allometric equation has an uncertainty. So you use that to model your LiDAR-derived height to biomass. And in your model, you have an uncertainty. So you propagate these two uncertainties when you get the estimate. So the uncertainty comes at different levels. First, the uncertainty comes from your allometric model itself. And the second, when you relate your LiDAR with the allometry-derived biomass, your model has an uncertainty. And then you use these two uncertainties and then get the final uncertainty estimate. These are just like normal linear models. Nothing really fancy, just the basic allometric models with your error term in there. The error you get from like usual regression approaches. Yeah.
Is there any standardized plot size for taking the ground data for the biomass estimation? That's
Yeah, there is. For Jedi, I think you need to at least have 0.25 hectare because it all depends on the footprint size. So for Jedi, the footprint size is 25 meter. So the whole 25 meter should fall within your plot. And you need to give plus or minus few meters for your uncertainty in the location because there is a geolocation uncertainty from the Jedi. So the basic, I think they really need minimum of 0.25 hectares of field size. I think that's even there in this slide from the conceptual. Yeah. So yeah, they can go from 0.07 to 25 hectare. but I think they really require a minimum of some size because of the footprint. Yeah, the Jedi footprint is 25 meters in size. So the whole 25 meters should fall within your plot, plus or minus the geolocation uncertainty of like few meters, like 10 meters. Yeah, thank you. Question.
Hi, thank you for the session. So I'm having a small curiosity.
Mhm.
I can be wrong also. So in the beginning, you started saying that this is a non-destructive method,
Mhm.
and we know that trees are not just species; it's a habitat for many other
Mhm.
species. My question is this laser? And I also read that these lasers are very destructive for insects and other lower species. So are they really non-destructive for other lesser invertebrates, or residing on the trees or others?
So yes, lasers can be destructive, but not all lasers, because these are class 1, which are actually tested for all the safety. So you're never allowed to use a laser which is actually damaging. So I don't really know, I can't say with certainty this is never going to have any effect on the invertebrate, but a lot of like forest, when you get permits and when you say laser, you are only allowed to use a certain type of laser and you're not allowed to use any other type of laser. And this has to be like a class 1 certified laser. So all the lasers that are used in forestry are all like class 1 certified laser. So they are supposed to be the safest form of these techniques. Because if you're not using a ground laser, you're always going to have like UAV LiDAR, airborne LiDAR has been in operation. So I think they are safe. They are not really destructive to invertebrates. I think probably we are more destructive to invertebrates by walking in the forest much more. Yeah.
So, ma'am, you told that lasers cannot penetrate the ground. Then how does LIBS is actually working? Like laser-induced breakdown spectroscopy is working, especially for identifying the soil carbon, soil fertility, and even the soil texture.
I don't really know if they really use laser pulses, because it could be something else. It could be other, because if you're only analyzing the spectral property, it could be a different sensor which penetrates, because light pulses cannot, because it's just a light, right? Laser is nothing else other than a light. So it technically cannot penetrate anything. If it can penetrate, you would be able to see what's behind this microphone. And all the lasers operate within the visible to max infrared, and none of these can penetrate anything. They are all reflected off the surface.
That is the dollar wavelength moving towards UV. So that's why.
Because it's possible that within the soil you have like small gaps, and these are penetrating those gaps. But yeah, as he said, you need much shorter wavelength and not longer wavelength.
Space research, we are using that this LIBS.
Okay.
Identifying the soil related characters.
I have no idea about what exactly they use. Okay. Maybe, as you said, they use a different spectrum which can penetrate even technique, not penetrate, but pass through different even smaller sizes. Because soils are just like small, minute particles, right? So they do have some gaps in them, which maybe we can't see, but other form of laser pulses can penetrate that.
I just have a small doubt.
Yeah.
You mentioned that you have done the scanning in 10 hectare area with 10 meters.
5 hectares.
5 hectares. So how much time did you take?
So what we do is we work with 2 people, and so every scan position, nowadays, the new LiDAR is much like the one that I used is 400, and now people use 400i, which is much faster. So technically for every position, it takes about, let's say 10 minutes, give or take. So in one day, imagine you take like 15 minutes because you still have to move to another location. So overall 15 minutes per position. And if you have like 20 positions to cover, then let's say 1 hectare. 1 hectare has like 100 scan points, right? So 100 into 15 minutes. It's like 1,100 minutes, 1,500 minutes. You should have to convert it into hours. Is anybody really quick with that here? I think about 2 to 3 days is what it will take, because you can't scan 24 hours. So you're scanning like 7 hours in a day, 6 hours in a day. 1 hectare takes 3 days, and then again binned. So you need wind-free 2 to 3 days to cover 1 hectare. If there is wind, then 4 days maybe.
And you have did it at 10-meter interval.
Yeah.
So that exact point is initially set up.
Usually these are
Standard.
all like long-term monitoring plots. So we actually follow, they're all like demarcated every 10 meters. We follow them the same direction in the north-south, and that's how we really follow. It's technically you can scan anywhere, right? Because you're still going to have the whole plot covered. But because we might want to do multi-temporal scanning, and we want to make sure that we scan from exactly the same positions, we always follow the plot markings. So we follow the trajectory of how the plot is laid out in the north-south directions.
Thank you.
Yeah.
I have a question. And the topic was very interesting. My question is regarding the pre-processing time. I know it's very painstaking to clear the noise out of the point cloud.
Yeah.
How much time does it actually take to clear one individual tree and to get the fine one?
This again really depends on what stage you're. If you're so used to processing this, a tree can be really fast. Let's say you can be done with the tree in like 10 minutes. Once you have, because you always get a basic from your algorithm, you're just cleaning up. So you can be done in 10 minutes. But I worked with a liana infested forest. So it's really horrible because you have to also cut out because I was interested in tree structure, which means I'm actually manually delineating lianas from the trees. So it took me really a long time, sometimes like an hour or two just for one tree if it gets massively infested. In a temperate forest, you probably don't really need that much manual cleaning because the algorithm itself can give you pretty good results. In tropics, yeah, a few minutes to half an hour, let's say, depends on how bad the outcome is. Yeah, so it's still quite a lot of effort that goes behind getting all the trees processed at this point. Yeah.
Yeah, so
Yeah.
Thanks for the presentation. And yeah, you may be aware that the use of structure-based indicators instead of taxa-based indicators and the tree microhabitats are very commonly used, especially in the temperate regions.
Yeah.
So one of my students recently did a study on tree microhabitats, probably the first one in Asia. And what she did was measured 21,000 trees in 12 hectares, and she identified 36 different microhabitats. And you can imagine the kind of field work on each tree we are doing it. So anyway, she completed it. So
this was like manually inspecting a tree and noting down the
yes,
different types of habitats on the tree. Yeah.
You may need one day for a tree also. Sometimes the microhabitats are so diverse. Then last year during Edindo's visit, I had an interaction with him.
Yeah.
How the new technologies are. Then he mentioned this and he suggested me to talk someone who really work on that. So now I understand that is pretty difficult because still some of the identifications are in the basic experimental.
Yeah. A lot of these new things are still, the most established thing is like the biomass estimates from LiDAR. So once you have the individual tree, that's like a gold standard way to estimate biomass now. But getting to the individual tree, we still are like struggling to get to that point. But microhabitat, there is already a work in microhabitat using TLS. Again, very experimental stage. Nothing that you can just say like, oh, I have TLS data, I'm just going to estimate microhabitat. No, we are not there yet. And that work was also done in temperate forest. Promising results, but not still scalable enough to,
And also other thing is applicability because of the cost. Is there any research happening on bringing down the cost of this actually? Because the thermal cameras are getting cheaper now.
Yeah, I'm sure it will get cheaper. But for instance, we recently purchased in Oxford this one, which is still pretty good, but it's half. Here I haven't mentioned the cost. It's not half, but it's almost half the cost if you don't buy a lot of like accessories. So this is what most people use for very detailed, and this is pretty new in the market, and it's really giving very good. It's comparable. The data is really comparable and at half the cost. So I'm sure, because academia is a very new thing for TLS, right? So these companies they market it for industrial to people, and they're never going to get the cost down for industries. That's how they make their money. But I guess now they see that more and more academia is using TLS, so there is a huge possibility for them to bring down the cost, because if this is so expensive, people are going to move to this one. I know already, like, there are few research groups which have purchased this just because they couldn't afford this one. So there is a really high potential for the cost to come down in the near future. But as of now, they used to give us academic discount before, because we were the first few people to buy. Our group was like the second or third one to buy this. So they gave a 10% discount. And recently I inquired for a new LiDAR because we were thinking between this or this. They don't give the discounts anymore. So I think they are now like, okay, we have enough people and we're kind of like monopoly here. If somebody wants the best LiDAR, they're going to come to us. So they're not giving the discounts. But I think with the introduction of this one, there is a chance that the price comes down a bit. Yeah.
Is there any optimal distance between the TLS and the treat subject to get a significant result?
It will depend on the LiDAR, the scanner that you use, but at least 1 meter. Most of the time the sensors will actually tell you like how far you have to keep your object from, because if you just keep it next to an object, yeah, you will either get no returns or you're just going to cover the massive tree there. So 1 meter to 1.5 meter. 1 meter is enough normally. Yeah.
If there is no more questions, I would request Dr. P.V. Saji to hand over a memento as a token of gratitude to our resource person.
I can come there. Thank you very much for participating.
Basically, I feel that we all here are connected to forestry, forests. We don't just study forests, we love forests. We are emotionally connected to forests. But you come from a totally different background, and that made the class so wonderful. Thank you very much.
Thank you very much for hosting me.
I request Dr. Balakrishnan, Head of Wildlife Department, for delivering the open thanks.
Yeah, we are slightly overshooted, and let me thank Sudhi for delivering a wonderful talk and explaining the evolution and answering all the questions of the girls and all whatever it is. Thank you. And thank Dr. Sajeev Andis for being here with the entire team and asking maximum number of questions, also making it live. And paper and Golden Jubilee Committee and the Seminar Committee. I thank our director for facilitating this, and thanks to all the participants, my colleagues, then students from Agriculture University, and big thanks to our technical team, and finally Surya for wonderfully coordinating this. Thank you all. Thank you.
Thank you very much for hosting me. Really nice to have this conversation. I really enjoyed it. Thank you very much.